Imagine waking up tomorrow to discover that every high-speed train in the world has been replaced by diesel-powered trains. At first, it might not sound like a disaster. After all, diesel locomotives have been hauling enormous loads for more than a century. They are still used in countries all over the world. But very quickly, something becomes obvious. The high-speed rail networks built to carry millions of passengers at incredible speeds simply stop working the way they were designed to. Trains can no longer reach speeds of 300 kilometers per hour. And inside long tunnels, another serious problem appears: exhaust fumes. Suddenly, an entire transportation system designed around speed begins to lose its purpose. The strangest part is that diesel engines aren't necessarily weak. Some can produce thousands of horsepower. The real problem appears when you try to use all that power at extreme speeds. So why couldn't diesel trains ever become truly high-speed machines? And what physical limitation makes electricity almost unavoidable once trains start pushing beyond 300 kilometers per hour? The answer begins with one of the oldest enemies in engineering: physics.
Imagine trying to accelerate a massive machine toward its absolute speed limit. You immediately run into a fundamental problem. A diesel engine produces enormous rotational force, but transferring that force through steel wheels at extremely high speeds is incredibly difficult. Think about riding a bicycle with multiple gears. When you're starting from a standstill, you use a large gear ratio that gives you maximum torque. But once you're moving quickly, you shift into a higher gear. Otherwise, your legs would be spinning wildly without making the bicycle go much faster. A diesel locomotive faces the same basic problem. It needs a transmission. But imagine trying to build a transmission capable of handling thousands of horsepower while operating at nearly 300 kilometers per hour. The gears and mechanical components would have to withstand enormous forces: friction, vibration, and heat. The faster you go, the more brutal the conditions become. And eventually, the mechanical system itself becomes the weak point.
To see this problem in action, let's go back to 1933. That was when Germany introduced an extraordinary diesel-powered train known as the Flying Hamburger. It was lightweight, aerodynamic, and powered by two powerful engines. The train could reach around 160 kilometers per hour, which was astonishing for its time. Passengers were amazed. Engineers celebrated what seemed like a technological breakthrough. But when they tried to push the concept even further, physics pushed back. As speeds approached 200 kilometers per hour, the mechanical components transferring power from the diesel engines to the wheels were exposed to extreme stress. The shafts twisted, the transmission suffered enormous vibrations, and the mechanical system was being forced to survive forces it was never designed to handle. Engineers had discovered something important. The problem wasn't simply producing power. The real challenge was delivering that power to the wheels at extreme speed. So they tried something radically different. Instead of using the diesel engine to mechanically drive the wheels, they turned the train into a giant mobile power station. And that created an entirely new set of problems.
The idea behind a diesel-electric train sounds almost perfect. The diesel engine doesn't directly turn the wheels. Instead, it spins a massive electrical generator. That generator produces electricity. The electricity then travels through heavy cables to compact electric motors mounted directly near the wheel axles. No giant mechanical transmission, no enormous gear system. Smooth acceleration, massive pulling power. It sounds like the perfect solution. But there is a catch. The generator itself is extremely heavy. Now the train has to carry the diesel engine, the fuel, the generator, and all the supporting equipment. A locomotive can easily weigh more than 130 tons. At low speeds, the tracks can handle this. But as speed increases, every bump and imperfection in the track becomes more significant. The heavier the machine, the harder it hits the rails. And the faster it travels, the more violently that energy is transferred into the track.
In 1993, a Russian locomotive called the TEP-80 attempted to challenge the limits of diesel-electric technology. During a unique test, the enormous machine reached an incredible 271 kilometers per hour. It became the fastest diesel locomotive ever recorded. Inside the cab, the noise was deafening. The instrument shook. The speedometer climbed higher and higher. For a moment, it looked like diesel technology had finally conquered high speed. But there was a problem. The tracks were struggling to survive. Sensors detected severe deformation. The enormous mass of the locomotive was pushing the rails into the track structure and generating powerful mechanical forces. The experiment proved something important. A diesel locomotive could be made to travel extremely fast. But operating a machine like that every day would place enormous stress on the railway infrastructure. The train might survive the speed. The tracks might not. And then another enemy appeared, one that no engine could simply overpower: air.
Above roughly 200 kilometers per hour, aerodynamics begins to dominate the battle. You can build the most powerful engine in the world, but eventually, the air around the train stops behaving like an invisible background. It starts behaving like a wall. The faster a train moves, the greater the aerodynamic resistance becomes. Think about walking through shallow water. At low speed, it feels easy. But try sprinting through that same water. Suddenly, the resistance becomes enormous. High-speed trains face the same principle, and the energy required to overcome aerodynamic drag rises dramatically with speed. To double the speed of a train, you don't simply need twice the power. You need dramatically more. At 300 kilometers per hour, a diesel engine would have to burn enormous quantities of fuel just to fight the air. And that creates another problem. The faster the train goes, the more fuel it needs. The more fuel it carries, the heavier it becomes. And the heavier it becomes, the more energy it needs. It's a vicious cycle.
In 1972, French engineers tried another approach. Instead of using conventional diesel engines, they created the TGV-001 experimental train. This remarkable machine used gas turbine engines derived from aviation technology. It was essentially a jet-powered train. During testing, the silver machine reached an astonishing 318 kilometers per hour. For a moment, it looked like the future had arrived. But the problem was economics. Those turbines consumed enormous quantities of fuel. The energy required to overcome aerodynamic resistance became incredibly expensive. Then, the oil crisis of the 1970s made the situation even worse. The cost of operating such a train became completely impractical. The project was eventually abandoned. Engineers were learning an uncomfortable lesson. Carrying your own power station and massive fuel reserves wasn't the answer. So they tried something much smarter. They decided to leave the engine on the ground and bring the electricity to the train.
Imagine removing the diesel engine. Remove the fuel tanks. Remove hundreds of tons of equipment. Now, instead of carrying all that weight, the train receives its energy directly from an external power grid. A thin copper wire runs above the track. The train connects to it using a device called a pantograph. On paper, the idea is incredibly elegant. But at extreme speeds, even this simple connection becomes a major engineering challenge. The pantograph has to maintain constant contact with the overhead wire. At low speeds, that's relatively easy. But approaching 300 kilometers per hour, something strange happens. The pantograph pushes against the wire and creates a mechanical wave. If the train moves faster than that wave can travel through the wire, the pantograph can temporarily lose contact. Then it slams back into the wire. The electrical connection breaks. A massive arc flashes across the gap, and the equipment can be severely damaged. So engineers needed to make the overhead wire behave differently.
When Japan prepared to launch its first high-speed railway, engineers faced this exact problem. Their solution was surprisingly simple in principle. The overhead wire had to be stretched extremely tightly. The tighter the wire, the faster mechanical waves could travel through it. Engineers installed massive tensioning systems along the railway. These systems constantly pulled on the copper wire, keeping it under enormous tension. The goal was to prevent the wire from sagging or developing dangerous waves as the train passed underneath. The result was a contact system that could maintain a reliable electrical connection, even at extraordinary speeds. This solved one major problem, but electricity offered something else, something diesel trains could never easily achieve: a completely different approach to weight distribution.
A traditional diesel locomotive has one massive engine at the front. That locomotive must be heavy enough to maintain traction with the rails. It then pulls a long line of relatively unpowered passenger cars behind it. Electric trains can do something much more clever. Instead of putting all the motors in one giant locomotive, engineers can distribute them throughout the entire train. Imagine a group of ants trying to move a giant leaf. If only one ant pulls the entire thing, it needs enormous traction. But if dozens of ants work together, the force is distributed. Electric trains use a similar principle. Compact electric motors can be placed beneath multiple passenger cars. Now the entire train becomes its own locomotive. This approach was brilliantly demonstrated by Japan's original Shinkansen trains. Instead of relying on one giant locomotive, multiple cars could contribute to propulsion. The result was smoother acceleration, better weight distribution, and improved traction. The train could accelerate rapidly without carrying one enormous block of dead weight at the front. But even this created a new challenge, one that appears when a high-speed train enters a tunnel.
At speeds above 300 kilometers per hour, a tunnel is no longer just a hole through a mountain. It becomes something much more dangerous: a giant pneumatic tube. When a massive train enters a narrow tunnel at extreme speed, it pushes a huge volume of air ahead of itself. The train behaves like a piston inside a syringe. The air has nowhere to escape quickly enough, so pressure builds up. A powerful pressure wave travels through the tunnel at roughly the speed of sound. And this creates a serious problem for diesel trains. A diesel train inside a long tunnel would have to deal with its own exhaust. The compressed air makes it much harder for exhaust gases to escape. The result could be dangerous fumes accumulating inside the tunnel and potentially affecting passengers. Electric trains don't have this particular problem, but they created another one. The pressure wave itself could become incredibly loud.
Japanese engineers discovered that high-speed trains entering tunnels could create enormous pressure waves. In some cases, the wave could emerge from the other side of the tunnel with a violent sonic boom. Local residents complained about the noise, so engineers looked to nature for inspiration. They studied the kingfisher. This bird can dive into water at high speed without creating a massive splash. Its long, pointed beak smoothly cuts through the surface. Engineers borrowed the same basic idea. They designed trains with long, sharply tapered noses. The extended nose gradually displaced the air instead of smashing into it all at once. This dramatically reduced pressure waves and helped high-speed trains move through tunnels more quietly. But even after solving the problems of aerodynamics and pressure, engineers still faced another invisible enemy: electrical arcing.
A traditional diesel locomotive has one massive engine at the front. That locomotive must be heavy enough to maintain traction with the rails. It then pulls a long line of relatively unpowered passenger cars behind it. Electric trains can do something much more clever. Instead of putting all the motors in one giant locomotive, engineers can distribute them throughout the entire train. Imagine a group of ants trying to move a giant leaf. If only one ant pulls the entire thing, it needs enormous traction. But if dozens of ants work together, the force is distributed. Electric trains use a similar principle. Compact electric motors can be placed beneath multiple passenger cars. Now the entire train becomes its own locomotive.
This approach was brilliantly demonstrated by Japan's original Shinkansen trains. Instead of relying on one giant locomotive, multiple cars could contribute to propulsion. The result was smoother acceleration, better weight distribution, and improved traction. The train could accelerate rapidly without carrying one enormous block of dead weight at the front. But even this created a new challenge, one that appears when a high-speed train enters a tunnel.
At speeds above 300 kilometers per hour, a tunnel is no longer just a hole through a mountain. It becomes something much more dangerous, a giant pneumatic tube. When a massive train enters a narrow tunnel at extreme speed, it pushes a huge volume of air ahead of itself. The train behaves like a piston inside a syringe. The air has nowhere to escape quickly enough, so pressure builds up. A powerful pressure wave travels through the tunnel at roughly the speed of sound. And this creates a serious problem for diesel trains. A diesel train inside a long tunnel would have to deal with its own exhaust. The compressed air makes it much harder for exhaust gases to escape. The result could be dangerous fumes accumulating inside the tunnel and potentially affecting passengers. Electric trains don't have this particular problem, but they created another one. The pressure wave itself could become incredibly loud.
Imagine a train traveling at 350 kilometers per hour. Above it, a high-voltage overhead wire supplies electricity. The pantograph must maintain contact with that wire continuously. But at extreme speeds, even tiny vibrations can create microscopic gaps. When the pantograph separates from the wire by even a tiny distance, electricity can jump across the gap. An electrical arc forms. The temperature of that arc can become extraordinarily high. It can damage the pantograph, it can erode the contact wire, and over time, the wire becomes thinner and weaker. This creates a constant battle against wear. Every kilometer of high-speed operation contributes to the gradual destruction of the contact system. And if a damaged component fails at 300 kilometers per hour, the consequences can be catastrophic. A broken pantograph can catch on the overhead equipment and tear down huge sections of the power system. One failure can bring an entire high-speed railway to a standstill. So engineers developed increasingly advanced monitoring systems. Modern inspection technology can detect tiny changes in the overhead wire before they become dangerous failures. But there was still one final physical barrier: the wheel itself. Every conventional high-speed train depends on one thing: a tiny contact patch between steel wheels and steel rails. The actual contact area of a wheel against the rail is incredibly small. At moderate speeds, that's enough. But as speed continues to increase, the limitations of mechanical contact become more important. The wheels must transfer enormous amounts of power through that tiny contact area. Eventually, traction becomes a problem. The motors can deliver more energy, but the wheels may simply begin to slip. You're putting megawatts of power into the system, yet the train struggles to accelerate further. So engineers faced a radical question. What if the train didn't need wheels at all? What if you could completely eliminate mechanical contact with the track? The answer was magnetic levitation. Maglev. Magnetic levitation removes the fundamental problem that has limited conventional trains for centuries: friction. Instead of steel wheels rolling on steel rails, powerful magnetic systems lift the train above the guideway. The train no longer needs to physically touch the track. No wheel impact, no rolling friction, no traditional mechanical contact. In 2015, Japan's experimental maglev train demonstrated just how far this technology could go. Using superconducting magnets cooled to extremely low temperatures, the train could levitate above its guideway. The train was no longer rolling, it was floating. Propelled by a traveling electromagnetic field, the experimental train reached an incredible 603 kilometers per hour, setting a world speed record for conventional rail-type vehicles. Inside, passengers experienced something completely different. The familiar sound of wheels striking rails was gone. The mechanical vibration was dramatically reduced. The train seemed to glide. Diesel engines will always have an important place in transportation. They are powerful, they are reliable, and they played a massive role in building the modern industrial world. For heavy freight and routes without electrification, diesel technology remains incredibly useful. But when the goal is absolute speed, diesel trains face a chain of unavoidable problems. Mechanical transmissions struggle with extreme torque. Diesel-electric systems become heavy. Heavy trains place greater stress on the tracks. Aerodynamic resistance grows rapidly with speed. Fuel consumption becomes enormous. Long tunnels create serious exhaust and pressure problems. And conventional steel wheels eventually approach their physical limits. Electric trains solved many of these problems by moving the power source off the train, distributing motors throughout the entire vehicle, and delivering energy through overhead systems. And when even steel wheels reached their limits, engineers went one step further. They removed the wheels entirely. That's the real story of high-speed rail. The diesel engine wasn't defeated because it was weak. It was defeated because the physics of extreme speed demanded something fundamentally different. At moderate speeds, diesel power is incredibly effective. But as you push toward 300, 350, and eventually 600 kilometers per hour, the future belongs to technologies that minimize